Introduction video to this section. We said that we want to talk about integrals over surfaces in the remaining sections here. Before we talk about integrals over surfaces, we need to figure out how to parameterize surfaces. So this video is going to be, and a lot of the rest of the videos in this section are going to be about parameterizing surfaces. So the idea here, before I give more formal definitions, let me do a couple of informal sketches here. So, okay, we might be thinking of a picture perhaps that looks like this. So we have X, Y, Z here, and we have some surface floating off here. And so the idea is that we want to come up with some ways to parameterize this with like a grid in terms of U and V. So we want to, U and V, or sometimes we might use other letters, theta phi, r theta, stuff like that here. But this is the basic idea that somehow we want to have these lines here correspond to in the UV plane. Let me draw in green so that matches up nicely here. So the idea here is that this surface in X, Y, Z in three-dimensional space corresponds to these variable, like this region here in the UV plane, with these red grid lines being actual grid lines over here. We need to figure out how to do this. That's one picture for me to draw. Let me draw a second picture here. It's going to be a little bit adventurous trying to do this in a video. I'm used to doing this demonstration in person here. But imagine that I take this piece of paper here, and I roll it up into a cylinder, and I orient it so that like this is the positive z-axis is, coming right at you into the camera here. And I want to have our surface be the surface of the cylinder. How could we come up with, let me say, this point right here? So this point that's right here, how are we going to parameterize this? Well, the idea is that, when I say that this is the positive z-axis here, like this is corresponding to z in some way, whereas if we move around the circle, this feels like polar coordinates in some way. This is corresponding to theta. And so a little moment's thought should convince you that, okay, if this is the entirety of theta and this is the entirety of z, this is like a rectangle in the theta z plane when I have it sitting down like this. But if I take then use this as our parameterization here and send it appropriately to the cylinder, it now becomes the surface of the cylinder here in X, Y, and Z space here. So there's two kind of pictures to draw to motivate what's going on. Okay, let's be a little bit more precise here. So our parameterizations are going to look like R of UV. So we don't always have to use UV, and we might use phi and theta, we might use R and theta, stuff like that, is some function of UV times I hat plus some function of UV times j hat plus some function of UV times k hat. So we want that to be a continuous vector function defined on some region R in the UV plane. That's 1-to-1 on the interior of R. We call the range of R the surface S. So to go back to this picture here, our domain in the theta z plane. And if you don't like me using theta and z, well, I'm just going to rename them u and v right there. Now done. Okay, so the region R here in the UV plane, this is R. When we do our map here to XYZ space, now this is our surface here. This is our surface. The range of R, the values that R can take on as U and V range over this region, big R, is this surface right here. The region here, this would be R in the UV plane, would be this square rectangle wherever, and then the set of all values take on under R of UV is this surface right here. If you take R of UV, this expression up here, this vector function, together with the domain R, that's what's called a parameterization, U and V or whatever letters you're using are going to be your parameters. Okay, so let's just find a couple of parameterizations now. So for example, find the parameterization of the cylinder. X squared plus y squared is equal to 9. Negative 3 is less than or equal to z is less than or equal to 5. Well, that sounds a lot like the picture that we were drawing here. So our cylinder is going to look like this. It's a cylinder of radius 3 centered on the z-axis going from negative 3 up to 5. So what if we want to say like this particular point right here, that's going to, on the surface, so we're talking about, this particular point here on the surface, there's a z coordinate to it. And there's also a theta coordinate. It tells you, this is theta is equal to 0. If this is theta is equal to 0, this tells you, and we're getting over to this point here, tells us what angle to form. So we're going to index this by theta comma z. No, there's no need for an r here. There's no need for r. Why is there no need for r? Because r is fixed to be 9. So we know we're thinking about this in polar coordinates. Oh, you're saying r squared is x squared plus y squared. R squared is equal to 9. R is equal to 3. This is not r is less than or equal to 3. This is not talking about the filled-in cylinder that includes the stuff inside the cylinder. This is talking about only things on the surface of the cylinder, and the surface of the cylinder, you're guaranteed to have r is exactly equal to 3 here. Okay, so what is our parameterization? R of, I'm going to use theta and z here, mimicking the book. Well, x squared, x in terms of, we know x is r cosine theta, but r is 3. So x is 3 cosine theta. Y is r sine theta, but r is 3 on the surface of the cylinder. So y is 3 sine theta, and z is just z. And so what are the bounds here on theta and z? Well, theta can be anything from 0 to 2 pi. We're doing a complete trip around the surface of the cylinder. Z is from negative 3 to 5.